All right, so to wrap up 7.1, I just want to go over example 4 on page 365 of your textbook. And it's basically doing an application of an addition of vectors, but with Cartesian vectors instead of geometric vectors, as we did in chapter 6. So we have a ship that's set to travel at 23 kilometers per hour on a heading of 40 degrees, so that's a true bearing of 40 degrees. And then we have, so this is the ship, and then there's a current in the water that is flowing at 8 kilometers per hour at a true bearing of, not at a true bearing of, from a bearing of. Remember, that's different. So we have to be really careful about that. So from a bearing of 160 degrees. All right. So first thing we need to do is convert these geometric vectors into Cartesian vectors, which is what part A of the question asks us to do. Sorry. Part A. So I'm going to start with the ship's velocity, and I'm just going to put that on my grid so I know where that 40 degrees is. True bearing of 40 degrees would be 40 degrees clockwise from north, or from 0 degrees, which is north. So it would be something like this. Okay. And then I need to find the components of that vector to write it as a Cartesian vector. So those components would simply be along the x-axis and parallel to the y-axis, tip to tail, to make up this ship's velocity vector. And so that means that the angle inside this triangle here is 50 degrees because it's complementary to 40 degrees. And so to write the ship's velocity as a Cartesian vector, my first component will be the horizontal component of this velocity, which is going to be the ship's velocity, 23 kilometers per hour, times the cosine of 50 degrees. And cosine because it is adjacent to the 50 degrees. And or you can think of it as the formula for writing a Cartesian vector from a geometric vector. It's in your textbook if you want to look it up. And then the vertical component would be 23 sine 50 degrees because it is opposite the 50 degree angle. So that is my ship's velocity as a Cartesian vector. Now I need to do the same for the current velocity. That one's just slightly trickier because it's from a bearing of 160 degrees. So remember how we do that. We draw at a bearing of 160 degrees, which would be here with an angle of 20 degrees, but instead of putting my arrowhead here, I turn it around and put it at the opposite end to make it from a bearing. Okay, now in order to break this down into components, I'm going to need to find the angle to the nearest x-axis. So I'm going to just slide this vector up here, right? And as long as it remains parallel or collinear, then it's fine. I can do that as long as I don't change its magnitude either. Sorry, I'm just fixing this because it was really weird looking and all squiggly. There, that's better. Okay. And so that means that this angle in here would also be 20 because it's the opposite angle to this one. But in order to break it up into components for the Cartesian vector, I want the angle to the nearest x-axis, so I'm going to put the components like this, or draw in the components like that, which means I want this angle inside the triangle, which would be 70 degrees. Now, in your textbook, they do it with 110 degrees. I find that really confusing to figure out why it's 110 degrees, and I just never can do that consistently, so I don't do it that way. But if you understand it, then by all means, go ahead. However, if you don't, that's not a problem. You can just do it the way I did it here to the nearest x-axis. So that's 70 degrees. Now, the only thing you need to be careful about here is you do need to be careful about the sign of the components. So let's just go back here a minute to part A. Notice that this component is going to the right or east. Therefore, it is positive. This component is going up or north. Therefore, it is positive. This component is now going to the left or west, and so we need to make it negative. So for the current, the first component is going to be negative 8, which is the magnitude of the current's velocity, cosine of 70 degrees. The second component is still up or north, and so we can just leave it positive, and it's going to be 8 sine 70 degrees. Now, the beauty of this is that if you've done all of this correctly and you have the correct Cartesian vectors for both the ship's velocity and the current, then it is quite a bit easier to find the resultant than it was with geometric vectors. So let's just go over to the next page. So what we have is that the ship's velocity as a Cartesian vector is 23 cos 50 degrees, 23 sine 50 degrees. And the current is negative 8 cos 70 degrees and 8 sine 70 degrees. Let me just double check that. Yes. Okay, so to get the resultant, all we have to do is add them, right? Because that's what we're doing here. We're adding the vectors to get the resultant. And so 23 cos 50 degrees plus, or minus in this case because it's plus negative, minus 8 cos 7 degrees is the first component. 23 sine 50 degrees plus 8 sine 70 degrees is the second component. So let's just put that all in the calculator. 23 cos 50. Make sure you close the bracket after the 50 if your calculator has a bracket there, otherwise you won't get the right answer. Minus 8 cos 70 degrees. So I have 12.048. Keep a few decimals here. And for 23 sine 50 plus 8 sine 70, I have 25.14. All right, now this is the resultant as a Cartesian vector. If we want to actually know the magnitude and direction of the vector, we'll have to turn it into a geometric vector. But we have some tools to do that now. The magnitude, we have a formula for that, is just the square root of the first component squared plus the second component squared. And so if you figure that out, it comes to approximately 27.9 kilometers per hour. Now for the direction, we're just going to have to sort of figure out what angle it is that we're looking for here. So if we go back to our diagram of the ship's velocity, which was somewhere here with 40 degrees there, and then, actually, no, sorry, wrong, erase that. all we have to do is draw this Cartesian vector on the grid. So 12.048 along the x-axis, 25.14 parallel to the y-axis, and then my resultant is simply the resultant of those two components. Okay, so all I'm doing is drawing this Cartesian vector as the horizontal and vertical components. And then of course I have a right angle there because they're horizontal and vertical. And so if I want to be able to name this, the direction of this vector as a geometric vector, I'm just going to need to find this angle in here. And I can do that with tan inverse of opposite over adjacent, which is, sorry I'm running out of room here, 25.14 over 12.048. Okay, squish, squish, squish. Anyway, if you do the tan inverse of that, you're going to get approximately 64.4 degrees. Okay, but to name the direction of this vector as a true bearing, what I really want is that angle in there. And that's just complementary to that angle, so I can just subtract it from 90 and I get 25.6 degrees. And so the final answer would be that the, sorry, what was the actual question? Determine the resultant velocity of the ship. So therefore, the resultant velocity of the ship is approximately 27.9 kilometers per hour at a bearing of 25.6 degrees.